The result which was obtained there was the formula for two-point correlation function or two-point correlator. This is the vacuum expectation value for the time-ordered product of two fields. So we have denoted omega as the vacuum state, so that the two-point correlator comes as follows. Here we have operators in the Heisenberg representation depending on space-time points x1 and x2. And this is the standard definition of the two-point correlation function coming from quantum field theory. But we have found the representation of this two-point correlator in terms of the path integral technique. It is equal to a limit, then time variable turns to plus infinity multiplied by 1 minus I epsilon of the ratio. Here we have path integral of the following form. The measure of integration comes over all possible trajectories, all possible configurations for scalar fields, phi x1, phi x2, exponent I s, where s is the classical action for real scalars. And here we have combination of exponent of I s over all possible trajectories of the scalar fields. Now, this combination is usually called as statistic sum sometimes, and s equal to the integral from minus to plus t for four-dimensional volume of classical Lagrangian density. So now we would like to develop some method to generate systematically all the relevant correlators. Not all just two-point correlators, but 3 points, 4 points, and so on and so forth. And all these correlation functions, in fact, are encoded in one main transition amplitude, from vacuum to vacuum. And here, to realize the method of generating this correlation function, we have to add in our system what is called arbitrary driving force, or just external source. And this method is usually called as generating function. So maybe physically, the picture behind the generating functional of correlation functions come as follows. By use of this arbitrary source, let's denote this source as G depending on space-time coordinates X, we create an arbitrary excitation of intermediate states that in its turn give us access to all possible correlation functions. But before developing this method, we have to add some technical tools. Namely, we have to understand how to use the so-called functional derivatives. Functional derivatives. So, turning back to the action, we have known that it is a functional of fields. In our case, we're talking about scalar field phi depending on x. And in a similar manner, a generating functional is a functional of these external driving sources j on x. And to extract the correlation functions from generating functional, which we will denote we will denote as double B depending on external sources G. We need to introduce the so-called functional derivatives. And the main rules, functional derivatives, comes as follows. If we have external source at point y, then the functional derivative of this external source at point y over external source at point x will be equal by definition to delta function of x minus y. Then, if we have the combination of integral over some y variables of j depending on y multiplied by some function of the coordinates y, and then we apply to this combination a functional derivative over the external source g at point x. That means, according to this main rule of the functional derivatives, that means that we have to take this functional derivative. It becomes delta function, integration over delta function multiplied by some function f leads to function f at the point x. And also, it should be clear that if we have some function of external derivative, let's denote this function as f denoted on j depending on y. And if we apply the functional derivative to this function of external source, delta j on x, that means that in this function, we have to replace separately for each external source, this external source by delta function of x minus y. Separately for each external source. Principally, functional derivatives is a sort of natural generalization of the rules for discrete vectors to a continuous function. And we can use the properties of the function derivative in the same way as for ordinary derivatives. That means that we can perform partial integration in this formalism. So if we take the functional derivative delta over delta j on x to the exponent of I integral d4 y j on y multiplied by 5 on y. That means that here we have in this combination, by use rules of the functional derivatives, result as imaginary unit multiplied by field phi at point x multiplied by exponent of I integral d4y j on phi at point y. And if we take the action of the functional derivative over j j on x on the following combination of the integral over y, here we have derivative of the external source at point y multiplied by field at the same point y. So the application of functional derivative together with the partial integration gives then the following result, minus derivative of the field at point x. But to make this result more or less mathematically correct, we have to add here the following symbol, PP, that from French means almost everywhere. Okay, so now let's form the generating functional for scalar field theory. And for scalar field theory, this generating functional W on G, which is nothing but the vacuum-to-vacuum transition amplitude at the presence of this external source G, equal to integral over d phi exponent of I integral d4x the Lagrangian density depending on our field and plus combination of field on source. J depending on X, on phi depending on X. And again, J on X is an arbitrary function that, in fact, excites an arbitrary field configuration. So now, by use of this generating functional, it becomes clear that principally some combinations related to the correlation functions, to be precise, to two-point correlation function, can be derived by functional derivatives of this generating functional over sources. And in fact, if we form the combination like minus imaginary unit, then functional derivative over source j at point x1. Here we have the same combination for the point x2. And if we will act by this kind of operators on our generating function, then according to the definition of this generating function and the rules of functional derivatives, we get the path integral of the following form. Here we get phi at point x1 on phi at point x2 on exponent of I integral over four-dimensional space-time of the Lagrangian density plus j on x on phi on x. And this path integral of this kind is one of the expressions which enters the definition of the two-point correlation function. That means that two-point correlator omega t product time ordered product of phi on x1, phi on x2, and omega can be rewritten in terms of this generating functional as 1 over double V from 0, the generating functional in the absence of any sources, multiplied by these derivatives, functional derivatives, acting on the generating function and the presence of sources. But in the end of our computations, to get the correlator, two-point correlator, we have to set sources equal to 0. And it is more or less clear that this result can be quite easily generalized to arbitrary correlation functions. It's clear that, for instance, the 4-point correlation function needs the action of 4 functional derivative over sources at 4 different points and so on. But by itself, we can express our generating functional by means of a sort of functional Taylor expansion as follows. Double V, depending on J, equal to double V in the absence of all external sources, multiplied by sum from 0 to infinity, I to the power of n over n factorial. Here we have integration from dx1 to dxn. Sources at points x1, xn, multiplied by n-point Green's functions, gn, depending on points from x1 to xn. And to get these n-point Green's functions, gn on x1 and so on xn, we have to apply the relative, the corresponding numbers of functional derivatives to get following result that will be inverse of the generating function at 0 sources multiplied by product from 1 to n of operators minus I delta over delta J at the corresponding points xi of double V dependent on external sources J. And in the end of computations, we have to set external sources equal to 0. So that these n-point Green's functions or propagators or correlators will be nothing but T-ordered product of fields at different points, x1, x2, and so on, xn. And this T-ordered product should be taken as the transition amplitude from vacuum to vacuum state. Okay, so now we have to take into account the concrete form of the action for the scalar field to compute the explicit form of the generating functional and to compute by this method endpoint correlators. Now, first example for that is to focus on free scalar field. So that let's take into account free scalar field without any self-interaction of fields. And therefore, the argument, the exponent of the generating functional is free scalar field. Then I on the classical action and the presence of source is I on integral of a four-dimensional space-time. We had add here the Lagrangian density for free real scalar field. This Lagrangian density is half of the combination d mu phi d mu phi minus half of m square phi square, where m is the mass of our real scalar field, and plus source term j on phi. Okay, so now to avoid some typical problems with mass shell of the field, I have to add to the mass the shift on small complex variable, so that with shift on I epsilon, where epsilon are real and small, I have integral over d4x half of d mu phi d mu phi minus half of m square minus I epsilon on phi square plus j on phi. And now I can perform the partial integration, and if I will set the appropriate boundary conditions, like for instance the absence of the field at infinity points, that will be equivalently I integral over d4x 1/2 of phi on minus d square minus m square plus I epsilon acting on phi plus source on the field. And here d square is nothing but the D'Lambertian, in fact, in four-dimensional situation, the combination like d mu on d mu. So now it's clear that introduction of this term make the integral convergent, and this is the main reason to introduce this small shift in the complex plane. Then we have the representation of this classical action functional in a quadratic form. That means that it can be integrated explicitly as integral of the Gaussian type. And to perform this integration, it is convenient to introduce the Green's function of this operator standing here, minus t squared minus m squared plus some complex shift, small complex shift. And by the way, this operator is called in the literature as Klein-Gordon operator. So that we would like to introduce the Green's function for this operator. Let's denote this Green's function as d dependent on x minus y. And then, by definition of the Green's function, the action of the Klein-Gordon operator minus t squared minus m squared plus I epsilon on d on x minus y gives us the imaginary unit I on four-dimensional delta function of x minus y. And it's clear that this function d depending on the difference between points x and y is nothing but the Feynman propagator of scalar field d x minus y is equal to integral over four-dimensional, say, dual to the coordinate space of the momenta I over a square minus m square plus this small shift I epsilon on exponent of minus I k multiplied by x minus y. And from this form of the propagator, it becomes clear the reason of introducing this small shift, because at the mass shell, then k squared should be equal to m squared for real, I mean, observed particles. The propagator without any shifts becomes singular. So this shift removes this possible singularity for real physical fields. And formally, then the Feynman propagator d of x minus y is the inverse of the Klein-Gordon operator, so that we can formally use the following relation between the Feynman propagator for scalar field and the Klein-Gordon operator minus d square minus m square plus I epsilon inverse. So now we have to compute a Gaussian type integral in the combination I s at the presence of external source. And to get the computations much simple, we can use the shift of fields. We can use the following transformation from the original fields phi to phi prime depending on x, which is the original phi minus I integral over d for y, the Feynman propagator dx minus y multiplied by the source j at point y. And according to this formal construction, we can equivalently say that we have here the following shift on the inverse Klein-Gordon operator acting on external source plus minus d square minus m square plus I epsilon inverse acting on j at point x. And if we insert this new fields phi prime into the classical action, then in the combination I s depending on external source, we can find that it becomes integral over x of 1/2 of phi prime on the Klein-Gordon operator plus I epsilon acting on phi prime and minus 1/2 of double integral, in fact, over x and y of the following combination, bilinear combination of sources and the Feynman propagator j at point x multiplied by the Feynman propagator d of x minus y j at point y. And for sure, we have to take into account the Jacobian of this transformation, but it is equal to 1, so principally this change of variables doesn't affect the measure of integration in the complete path integral. But at the same time, if we will take into account the integration over phi prime here in the complete expression for for the path integral, we can observe that this integral is not well defined because it leads to new dependence on external sources, and this dependence comes to some normalization factors and so on. But principally, when we will use this path integral to compute correlators, it turns out that all not well-defined things will be omitted due to the structure of the correlation function, as the ratio of something and statistical sum. So in free field case, then the generating function becomes as follows. So we have double V 0. 0 is the indication of absence of self-interactions of our scalar fields. So this is indication that we're talking about free scalar field. Double V0 depending on external source J sources. Turns out to be double V0 in the absence of these sources on exponent of -1/2 integral over 4-dimensional x and y of this combination, the linear combination of sources and the Feynman propagator. So to make our notation compact, I will write down this expression as exponent of -1/2 j x dxy on jy. Okay, so this is the time to get a long rest for 10 minutes, and let's take this break and we'll continue after that. Okay, let's go ahead. So before before continuing further, let me point out the following point on the expression encoded at W0 at zero source. So explicitly, this generating functional W0 at zero source is equal in terms of our new fields phi prime as integral over all possible configurations of these fields phi prime on exponent of I over 2 integral over four-dimensional space-time. Here we have phi prime multiplied by the Klein-Gordon operator minus d square minus m square plus I epsilon acting on phi prime. And here we have some analogy with finite-dimensional Gaussian integrals. I recall that in the finite-dimensional situation, integrals like the product of integrals in the following form: exponent of minus 1/2 of xi in some matrix b a j x j becomes proportional to the determinant of this matrix B to the power of minus 1/2. So formally, we can denote this combination corresponding to the generating functional at zero source as W0 at 0. And if we will apply the technique that have led to this result, it will be something like minus square, the inverse square of determinant corresponding to the Klein-Gordon operator. Determinant of d square plus m square minus I epsilon to the power of minus 1/2. And principally here we have to take into account many issues related to computing, even formal or non-formal computing of determinant of the operator, because we have to prove first that this determinant is a sort of a positive quantity. The next point, that this determinant converges. That means that principally the number of eigenvalues for this determinant could be possibly infinite, and that more important, we have to take into account quite correctly the so-called zero modes of this operator, the Klein-Gordon operator, corresponding to to the conditions, then determinant of this operator is equal to 0. So that in many applications, in the most, to be concrete, applications, the explicit expression of this determinant of the operator is irrelevant, but becomes important when we will try to figure out some special so-called topological properties of the vacuum or the properties of the zero modes and so on. So principally, the explicit form of W0 with zero source will not be so important for us, our situation. So then with the explicit expression for V0 depending on the external source, we can compute the 2-point correlation function then. So if we denote the vacuum as usual as state 0, then 2-point correlation function T on phi on x1, phi on x2, 0 turns out to be I square on functional derivative over first source, second source. That means sources at points x1 or x2, acting on the exponent of minus 1/2 of jx dxy jy, and to compute the correlator, we have to set j equal to 0 in the end of our computations. So again, this combination jx dxy jy is nothing but the double integration over 4-dimensional x and y of combination j dependent on x on dx minus y on j dependent on y. So that we have to take into account the explicit form of this notation in forming the functional derivation. So we can continue here. To get the application of the first functional derivative over J2 minus coming from square of the imaginary unit minus d over dg1 of minus 1/2 d to y on jy minus 1/2 of jx dx2 on exponent of minus 1/2 jx d x y j y at j equal to 0. It's clear that the first term comes to the action of this derivative here at the first source, external source at point x, and the second term comes from the application of this functional derivative over source at point 2 at the external source at point y. Then taking the second derivative and setting that after that j equal to 0, our final result will be 1/2 of d1 2 plus 1/2 of d2 1. That means that we have 1/2 d of the difference points x1 and x2 plus 1/2 d on the inverse difference x2 and x1. But this sum is nothing but the definition of what is usually called the Feynman propagator. So that this is d depending on difference between points x1 and x2. Feynman propagator. So in this way, we have reproduced the well-known result that the Feynman propagator is nothing but the two-point correlation function. But in terms of the functional derivative and in terms of the path integral technique. So now let's figure out what will be a result of 4-point correlation function. And by the way, it's more or less easy to see that the odd point correlation function in this situation will be equal to 0. So it's quite unreasonable to consider the trivial result for 3-point correlation function. So the next non-trivial result can be obtained for 4-point correlation function. So again, by definition, 4-point correlation function is the vacuum-to-vacuum transition amplitude of T-ordered product of field operators at 4 space-time points, x1, x2, x3, and x4. By definition, it is equal to imaginary unit to the power of 4. Then we have to use 4 functional derivatives of the external sources at different points. Let's denote these points as 1, 2, 3, 4. And we have to apply this construction, these parameters, to exponent of minus 1/2 jx dxy on jy and set j equal to 0 in the end of calculations. So now this factor is equal to +1. Then doing step by step, we will apply the first functional derivative to this exponent. Then we get the following result: minus jx on dx4 exponent of minus 1/2 jx dxy jy. Okay, so the next step is to apply this functional derivative to this combination jx dx4 exponent. The result will be minus d3/4 plus jx dx4 jy dy3 exponent of minus 1/2 jx dxy jy at j equal to 0. So the next step is to take the functional derivative over g2. Here we have d3/4 jx dx2 plus d2/4 jy dy3 plus jx dx4 d2/3 on this exponent minus half jx dxy jy at g equal to 0. And finally, was taken into account that we had to set the external source j equal to 0. And the end of computations, the final result comes as follows. D3/4 D12 plus D2/4 D13 plus D14 D23 3. And clearly, we have 3 terms, each of which contains 2 disconnected contribution, because here we have 2-point correlators. And principle of this result can be illustrated with a sort of Feynman diagrams. If we denote pictorially the Feynman propagator between points x and y as line connecting x and y, then the so computed Green's function or 4-point correlator G x to x1, x2, x3, x4 by our computations comes as d3,4 on d1,2 plus d2,4 on d1,3 plus d1,4 on d2,3, so that this Green's function then, in terms of propagators, turns out to be as follows. Now, first term, for example, will correspond to the following diagram. We have 2 correlators connecting points x1, x2. This is the first one, and the second one is the propagator related to connecting the points x3 and x4. So keeping the points x1, x2 to be always on the same position. Then for the second contribution to the 4-point Green's function or to 4-point correlator, then we have connection of points 1 and 3 and 2 and 4, and plus the rest, so x4, this kind of product of 2 propagators. We have to connect points 2 and 3 and points 1 and 4. That means that there is no any crossing between these 2 lines. And in the free field case, then this denominator becomes trivial from the point of view of having no any no any contribution to the 4-point Green's function. Now, taking into account this picture, we can say that we're dealing just with 2-point connected Green's functions, because these lines connect just 2 points, 2 different points. So to figure out the relation of the concrete situation to the connected Green's function, we have to introduce another type, generating functional, related to W dependent on J through logarithm or exponent. To be precise, let me introduce the functional Z dependent on the external source, which is related to the have determined generating functional W on the source J as exponent of I on this Z depending on J. That means that turning back to free case double B0 depending on J is equal to double V0 in the absence of of any external sources on exponent of -1/2 of Jx Txy Jy. It's clear that functional Z0 depending on J multiplied by the imaginary unit I equal to -1/2 of Jx Dxy Jy plus a constant related to having this contribution of double V, double V with zero source as this constant. And again, I will recall that in our notation, this Jx Dxy Jy is nothing but integral over x and y of the combination, which includes external sources at points x and y, and the propagator, Feynman propagator in this case, between these points x and y. So now, as in the case of double V dependent on J, we can perform a sort of Taylor series for the functional Z dependent on J and I Z dependent on J, then turns out to be some from 0 to infinity with I to the power of n over n factorial. Here we have integral, multiple integrals over dx1 dxn, and then the product of external sources at different points x1 xn multiplied by connected, this C for connected n points Green's function xn. In the free field case, we have just 2-point correlators, 2-point Green's function in this series, because we deal here just with these non-trivial correlators corresponding to the Feynman propagator d x minus y, and the rest of the connected Green's functions for n greater than 2 in this series expansion for z functional turns out to be equal to 0. Okay, so that is what concerns the free scalar field case. Now let's introduce the interaction, and let's study the case of self-interaction for real scalar field. Let's understand what will change with introducing the self-interaction. Path integral for interacting scalar field theory. We will consider the interaction at the level of the Lagrangian density as adding to the free field Lagrangian density, which we will denote as L0, some potential depending on fields. And for the real scalar field, L0 on phi is nothing but 1/2 d mu phi square, which is equivalent to d mu phi minus 1/2 m square phi square. And here I could say that principally this is the matter of taste, what the sort of this part of the even free action will be, the sort of self-interaction, because we have phi square here, the sort of part which is related to the free Lagrangian. But traditionally, in the case of the scalar field theory, we will consider this formal self-interaction part is phi square as the part of free Lagrangian density. And then, as in before, the generating functional W depending on external sources is denoted by the vacant to vacant transition amplitude and the presence of this non-trivial source or sources. And this generating functional in terms of the path integral is denoted by integral over all possible configuration over real scalar field phi on exponent of I integral d for x, and then here we have lambda, which will include here interaction term lambda on phi plus term with external source. And now the point is how to obtain double V on G explicitly. So to this end, it is convenient to note first that if we apply the the functional derivative over external source at point y n times to exponent of I integral d for x j x fx. The result of the application of this sort of operator will comes as the nth power of phi field at point y to the power of n or exponent of I integral d for x j on x on phi on x. So now suppose that we have some general analytic function. To be precise, it should be functional of the scalar field phi on x. And let's denote this analytic functional as f depending on phi. So now, if we introduce the following shorthand for integral over t for x jx phi x, then f depending on phi can be reproduced from the following combination. If we set here exponent of minus I j phi, then we will form the corresponding to the form of this functional f depending on operators instead of the fields. And let's act by this functional of of derivatives of the external sources on exponent of I j phi. Then, as in the previous example, this result will be reproduced as taking this functional of derivatives on exponent of I j phi at j equal to 0. So the last line can be used in our computations of correlation functions from the generating functional by use of functional derivatives of the sources, and this form can be applied in the case that we have non-trivial interaction, self-interaction field. So we've taken this into account, that the form of say potential depending on fields can be reproduced as potential when fields are replaced by operators. It allows us to write down the generating functional as integral over possible configurations of our real scalar field. Then instead of exponent of the potential of self-interaction, we can use exponent of minus I, and here we have V, the explicit form of our self-interaction of fields, and instead of fields, we will use here now functional derivative over source at point x, and this operator will act on exponent, which will contain the free Lagrangian plus part related to the interaction of our fields with external non-trivial source. And this part, this exponent, in fact, is nothing but the generating functional for free fields. That means that the generating functional in the case of non-trivial interaction can be reproduced by use of the action of this exponent, the operator exponent, including the non-trivial potential, Jx on exponent of minus 1 half jx dx y jy on double E 0 with zero source. And as I have said, this combination is nothing but the generating functional in the case of free fields. So that again, what we have to use here is the known form of the generating functional for free fields and the special operator encoded into exponent and the explicit form of the self-interactional fields. And instead of fields here, we have to use the functional derivatives of the external sources. Okay, so this is the time to get the short break for 5 minutes, and let's take this break and we'll continue after that. Okay, so now it will be important to realize what the sort of potential we have to take into account. I mean, the function v depending on phi. Since it could be strong or small, in fact, perturbation from the point of view of free configuration. And in what follows, we will suppose that the interaction of fields is a sort of small perturbations. That means that principally we will use a sort of perturbative expansion of this exponent, operator exponent, near 1. And to do that, first let's present the later expression in the absolutely equivalent form. So double V depending on J equal to double V 0 on J. Here we have 1 plus double V 0 on J multiplied by this exponent, special exponent, in which our potential is nothing but something functional with functional derivatives over external sources minus 1 multiplied by double V 0 on J. And now in terms of Z functional, recall that V and Z are related through the exponent of I, Z, J. Then in terms of this Z, this sort of representation tells us that the Z functional in terms of interacting fields is the sum of Z functional for free field plus some constant coming from this constant related to V0 at 0 sources plus logarithm of 1 plus exponent of minus I Z0 depending on external sources. Here we have the same operator as in these square brackets, exponent of minus I V depending on minus I, a functional derivative over external sources minus I applied to exponent of I Z0 depending on external sources J. So for now, we would like to apply this general scheme to the potential V equal to lambda over 4 factorial by 4. And because we would like to use perturbative expansion here, we have to look at this potential as a small perturbation over free field. That means that constant lambda, the constant of interaction, in fact, the self-interaction of real scalar fields, will be chosen to be small. Okay, if this lambda is small, then operator here, the exponent of minus v minus 1, or small lambda, exponent of minus I, we have corresponding integral with functional dependence of our potential minus 1. Then again, in terms in the case then lambda is small enough, this exponent turns out to be minus I lambda or factorial integral over some four-dimensional variable z minus I to the power of 4 and the fourth power functional derivative over external source plus all of lambda squared. So again, this integral and the operator inside of this integration is nothing but the corresponding representation of our potential in term when instead of fields we have the combinations of the functional derivative over external sources. And in z on j, we're dealing with logarithm, the corresponding logarithm of 1 plus something, then turns out to be, in the case of small lambda, to the minus I lambda over 4 factorial on exponent of minus I z0 depending on j, and here we have the integral over four-dimensional z with fourth power derivative over sources acting on exponent of I z0 depending on j, again up to terms of the next power in lambda. Okay, so now let's figure out what is this integral with fourth power derivative applying to exponent of I z0 depending on j. And here I will recall that IZ0 depending on J is nothing but the combination minus 1/2 Jx dxy jy. That means that we have to compute the action of this first derivative to exponent of this combination. Okay, to make it explicitly, let's do it in step-by-step manner. Delta J dependent on the force on exponent of minus 1/2 Jx dxy jy. So the first step, first functional derivative over an external source at z point leads to a following combination minus minus dxz jx on exponent of minus 1/2 jx dxy jy. Further, applying the functional derivative over g at point z twice, we have t4z, then here the rest is the second derivative over jz acting on the combination minus dzz plus dx zjx dy jy on exponent of minus 1/2 jx dxy jy. In the next step, we have integral d4z functional derivative over g at point z should act on d z z d y z j y plus 2d z z d y z j y minus dx z jx dy z jy d a z j a multiplied by exponent of minus 1/2 jx dxy jy. And finally, then we get the following combinations of the propagators. 3 dzz square minus 6 dzz dyz dxz jyjx plus dxz dyz daz dbz jx jy jab multiplied by exponent of minus 1/2 jx dxy jy. So how we can present the expression inside the square brackets in the pictorial form. This expression three dz square minus and so on, by the way, on exponent of minus 1/2 jx dxy jy can be presented as the first combination is the combination of two propagators which begin at point x and will end at the same at point z, sorry, and will end at the same point z. So with the factor 3, it will correspond to the following picture. Let's denote this propagator as this dashed line, and we have here the combination of two propagators which start and which starts and ends absolutely in the same point. The next combination inside of these brackets with factor minus 6 will correspond to the following following combination of correlators and external sources at points x and y. So let's take these points x and y and external sources here, j and j. Then in this this combination, we have propagator from point x to point z. Let's say this z point something here, and this propagator from x to z comes as follows. Then also we have propagator from point y to z. And we have propagator which starts and ends at point z. So again, we have a loop here. And also with weight equal to 1, we have the following picture of external sources at points x, y, a, and b. So here we have points x, y, and a, and b, and everywhere we have external sources at these points. And we have midpoint z, which is related to every of the points x, y, a, and b with the corresponding propagator. Here we go. So principally, as we can see, in the case of self-interaction and in the case of z-functional, we are dealing with the connected Green's functions. So all the points at these diagrams are connected through the Feynman propagators to each other. And therefore, the final result for the functional z dependent on j in the case of phi-4 theory, because this is not the final result. It is the result of computation, just one piece of this functional. For z, then, to be precise, for I multiplied by z dependent on j, we then have this constant minus 1/2 j x dxy j y, and minus the result coming from the self-interaction I on lambda over 4 factorial on 3 dzz square minus 6 d z z dy z dx z j jy jx plus dx z dy z daz db z jx jy ja jb. And again, this result is up to the second derivative in lambda constant of interaction, self-interaction of our field. So now, principally, to get the functional double V dependent on J, we have to exponentiate the result, this result for the functional Z on J. And therefore, for this double V on J, We then get by exponentiating of this expression for z on g, instead of constant here, we will get double v0 depending on zero sources, on exponent of minus 1/2 of j, say alpha on d alpha beta on j beta, multiplied here on 1 minus I on lambda over 4 factorial multiplied by 3 of the following diagram minus 6 of the diagram with two sources, and I'll loop inside and plus the diagram corresponding to 4 sources, point Z, JG, JG. Again, this result up to the second order in lambda constant. And now we can renormalize, in fact, double V0 depending on zero source on this diagram, on two bubble diagram. That means that we can absorb right this sort of diagrams into the normalization double V depending on zero sources, because it's clear that we have no sources here, so that the result for double V depending on J will be presented as double V depending on zero sources on exponent of minus 1/2 J alpha D alpha beta J beta on 1 minus I lambda over 4 factorial on this diagram with 4 sources J, 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 plus I lambda over 4 on the diagram with just 2 external sources. Here we have a single bubble here plus terms of the second power in lambda. And explicitly, this double V on 0 an exponent of minus half of J alpha D alpha beta J beta on 1 minus I lambda over 4 factorial d x z d y z d a z d b z j x y a b plus I on lambda over 4 d z z d y z d x z on j x gy plus terms of the second power number. So what we can say, according to absorbing the diagrams without any external sources into the new normalization, we can say that double V0 depending on zero sources corresponding in fact to term which is related to the vacuum state. This term will transform into double V depending on zero sources. That means that this term will correspond to the vacuum now in the interacting theory. So we can say that, at least formally, the vacuum of free theory and interacting theory are not the same. And principally, now from the obtained double V on J functional, we can compute 4-point correlation functions G depending on x1, x2, x4, x3, and x4 over the same technique as seen before. But principally, it will lead to the same result as in the free case with the insertion of interaction and the corresponding order of perturbation. That means, for example, that at the level of 4-point Green's function, diagrammatically, the result will look as follows. So for 4-point Green's function, we then will get at the first order level of consideration over the lambda interaction coupling constant. So we will deal with following sort of disconnected diagrams. Then we'll get here diagram of the following form, where at this point we will insert an interaction constant like that, and also because we are dealing with 4-point Green's function, we will get these sort of diagrams with 4 external points. And also we should add all possible permutations with respect to the points x1, x2, or x3, and x4. And at the first order, we should add also the following 4-point diagram or external point diagram. x1, x2, x3, x4 with insertion here in the midpoint, the combination of the interaction constant minus I lambda. So this is the main result, at least at the first order perturbative expansion over the small coupling constant lambda. Okay, so let's stop for now here. And if you have questions, please go ahead. Do you have any questions?
I have no questions at the moment.
I also don't have any questions.
Okay. So if you have not any questions, thank you for coming, and see you tomorrow. Bye-bye.
Thank you. Goodbye.
Thank you. Goodbye.